Now that we've plumbed the depths of kinematics, which is a description of how things move without regard to their cause, it's kind of time to start talking about the cause of why things move certain ways. Our first approach to that's going to be something called dynamics, the study of forces and how they interact with objects. Here we have a cartoon that's sort of making fun of a thing we'll learn later in this chapter, which is Newton's 3 laws. Is this exactly right? Not exactly, but it's meant to be funny. This all dates back to a person named Isaac Newton, who you may or may not have heard of, but he really is the guy to blame for all of this. He lived from 1642 to 1726. He was at the edge of the beginning of the Enlightenment, right when things started transitioning to what we would call modern science today. In fact, we often date modern science from Newton's work. He was a philosopher and a scientist. He was the warden of the mint. Someone once called him the last of the magicians and the first of the scientists. He was into the occult. He studied the Bible as assiduously as he studied planetary motion. He was looking to organize the world, to make what he called a system of the world. And he made a lot of progress, and there's a reason why his fingerprints are all over things we're going to be doing. To understand the motion of the planets, which was his ultimate goal, he found that he needed a better understanding of motion in general. And to describe motion, he had to invent a branch of mathematics, which is called differential calculus. To understand orbits, he had to invent another branch of mathematics, which is integral calculus. And he caused at least one person to be hanged until dead. So he had quite the life. Newton's insight is codified into what's called Newton's 3 laws of motion, usually called just the laws of motion. And we're going to study them in sequence, obviously. The first law of motion is relatively easy to state. An isolated object maintains a constant velocity. Isolated here means that the object does not interact with any other object. Right? So it means what you would think it means, all alone by itself. From textbooks, we get things like an object has no forces on it, then if it is at rest, it will remain at rest, and if it's moving, it will continue to move in a straight line at a constant speed. If you think about it, those are the same statement. The second one is just more complicated and involves things we haven't talked about. We haven't defined what a force is yet, so that doesn't really help us any. And then, of course, remaining at rest or moving in a straight line at constant speed is the same as saying maintaining a constant velocity. So in my opinion, this is the superior way of phrasing the law. It's clean, it's short, it's easy to remember. An object that is isolated maintains its constant velocity. But everybody quotes the other one because that's how they learned it from their textbooks. This is also known as the law of inertia, because inertia is a property of objects that says they tend to maintain a constant velocity. The word inertia, I think, interesting enough, comes from the Latin for laziness. Objects are lazy. They don't change their velocity on their own. Inertia is demonstrated by, for instance, somebody jumping into a pile of leaves that are on a trapeze. And you can see the person has come through, punched through here. There they are falling. But the leaves are still in place, even though they're not held up by anything. They have not yet had a chance to start falling because their inertia keeps them in place until a force acts on them. So, and the force is gravity, so the acceleration is smooth but somewhat smallish, and so it takes a little bit while for them to get into serious motion. The full clip of this is linked on the website and is worth watching. It's only about a minute, and it's kind of impressive. Then we say the reference frame is said to be inertial if the first law holds in it. Otherwise, the reference frame is non-inertial. In fact, the first law is really less a fundamental law in and of itself. It's more a device to characterize frames of reference. Only when the first law holds are the other laws also guaranteed to hold. So it's a little weird to call it a law of motion. It really should say in an inertial reference frame, an object maintains constant velocity when it's isolated. When would you be in a situation where that's not the case? Well, say you're driving down the highway at a pretty high speed, you've got a cup of coffee on your dashboard, and you make a sudden sharp right turn. From your point of view, the cup doesn't maintain its constant velocity. It slides across your dashboard towards the outer part of the turn. But you're not an inertial reference frame yourself because your car is turning, so you're accelerating. So if you're using like your steering wheel as your origin, it's undergoing acceleration, and Newton would say that's not inertial. So you can't use my laws because the first law doesn't hold. Another example on the same line, a car where the brakes have suddenly been activated. In that frame, a still object will leap forward even though there's nothing acting on it. But it's not really leaping forward compared to somebody who's outside, say in a helicopter watching from above. They see the cup just continue moving at its original velocity. You see it leap forward because your reference frame suddenly accelerates the other way. All right. One thing acts on another by exerting a force on it. That's what we're saying. The interaction of two objects are mediated by forces they exert. You can think right now of a force as a push or a pull. If we add up all the forces on a given object, we get the net force acting on it. Net force is just defined as the sum of all the different forces. We'll have to keep in mind that every force is a vector. It matters which direction you push or pull something. And so the net force is a vector as well. When we add the forces, we're going to add them vectorially using tip-to-tail formulation. The study of the interaction of things via forces is called dynamics. And that's because dyne is the Greek word for force, or the ancient Greek word force. It tells us why things move the way that they do, as opposed to kinematics, which tells us the manner in which things move but does not explain why. Because the Greek letter sigma is often used to stand in for sum in mathematics, we can symbolize the net force in two ways. We can write F sub net with a little vector on it, say its vector sign, or we can say the sum of all the forces, and this whole thing together is the net force, that this construction is the net force. Different textbooks use different notations, and we'll pop back and forth between these two. The committee also pops back and forth between these two, so we'll get practice with both. An illustration of inertia comes from an impact of a car with a wall, and we'll watch the crash test dummy that's in the car. At the instant before impact and at the moment of impact, the car and driver are moving at the same speed. The car, though, slows as it hits, but since the driver is not connected to anything, there's no forces acting on it from the car, so the driver continues at the same speed until they hit the dashboard, and then the dashboard exerts forces on it and stops it. And again, there's a short clip online that shows this thing in slow motion so you can see it, but the key thing is that the inertia of the driver keeps it moving forward. This is, by the way, meant to demonstrate the use of safety restraint devices such as an airbag or a seatbelt, whose main role is to exert forces that that decrease smoothly rather than being sudden, so that the object decelerates smoothly instead of in a quick impact. All right. Features that are common to all forces. A force can be thought of as a push or a pull. Notice we're not saying what's the mechanism yet, and we'll talk briefly about that later in the class, but it's not that important. It's just the interaction that is a push or a pull on something. A force will act on an object. Forces aren't disembodied. They are acting on something, and they're being generated by something. Every force has an agent. That's the something that acts, the something that pushes or pulls, the thing that generates the force. A force is always a vector. The general symbol we'll use is the vector symbol F with an arrow over it. The size or strength of this force is its magnitude, and following our earlier convention, if we drop the vector sign, we mean the magnitude of the thing. Contact forces are forces that act on an object by touching it at a point of contact. Sort of, we're not that great with naming things. So when the ball hits the bat can exert forces on the ball while they're in contact. Once the ball leaves the bat no longer influences it. There are also long-range forces that act on an object without any apparent physical contact. For now, the only non-contact force that we will consider is gravity. The others are things like electromagnetism, and some of the nuclear forces are non-contact. But they're esoteric and weird and hard to do, so we're going to put them on the side. On the other hand, we really can't do stuff on Earth and not deal with gravity, so we're going to have to include that. It will be our only non-contact force. If you're going to draw a force vector, you'll represent the object as a particle, place the tail of the force vector on the particle, and draw the force vector as an arrow pointing in the direction the force acts, and with a length proportional to the size of the force. Again, here it's just a vector, so its length is proportional to its magnitude. But start at the object and push away, and then, of course, give it some sort of label. This is a little pedantic. This is not entirely how people sort of in the wild do it, but it is the way the College Board expects you to do it, so we're going to try and be consistent with that notation. Life isn't destroyed if you have the arrow pointing, if you have instead the arrow pushing on. If I had that baseball, and here's my baseball, and I want to say that the bat pushes it, to me it is more intuitive to say that the force looks like this. But this tactics box is correct in that the College Board generally will state have the arrow start on the object and point away from it. So we're going to practice that as well. All right, let's try this one. The net force on an object points to the left. Which two of the three forces that are acting are shown? What is the missing third force? All right, so the net force points directly to the left. Our net force points like this. So I need to be able to take an upward vector and a sideways vector and some third vector to point to that. You can kind of do this intuitively and say, well, we have to have a vector that points, it has to have a component opposite to the upward force so as to cancel it, and a horizontal force which is equal in length, actually a little bit longer in length horizontally, so that when I add these 4 vectors, we'd end up canceling out the vertical part and having some horizontal part. Of course, for real, they want the vector that comes out, so I'm going to have to add these. Luckily, they're already tip to tail, and so I can draw just, oops, this would be the sum, so that would be F3. So it looks like it should be C, more over than down. And we see a nice artist-generated version of that rather than my little scribble.